You might be confused by the title for this video, but the problem of proving root 2 to be irrational is such a classic problem with such a classic solution that it's kind of hard to motivate another method for proving this result. However, this method is very powerful and very much worth learning for solving harder problems. Problems that are way harder than this. So, this technique is called proof by infinite descent. I'm going to write it on the board. Just solely on the name, you might be able to make some sort of guess as to what this technique involves. You can take the analogy of someone who does not think that a black hole is that dangerous, okay? So this person claims that it's only so dangerous, we can only get pulled within X meters to it, okay? Now, you can say, okay, suppose that you are right. We can only get pulled to that X meter mark. Now, I'm going to prove to you that at that X meter mark, it's possible to go closer, maybe like X minus 1 meter mark, right? So you can make that proof, and then you can prove that at any mark that you can, that you think is the limit, it's always possible to go closer, and you can repeat that process indefinitely, thus proving you can go infinitely close towards a black hole, and therefore a black hole is really dangerous. So let's see that in action for this problem. Based off our analogy, it seems smart to start off with proof by contradiction. So we're going to first assume that square root of 2 is rational. So therefore we have that square root of 2 is equal to p over q, where p and q are positive integers. Now we're going to square both sides. So we have 2 is equal to p squared over q squared. Now I'm going to make another assumption. Because we assumed that there exists positive integers p and q that satisfies this equation, we're going to assume that the specific solution pair of p, q is the solution pair that minimizes the sum of the contents. So therefore, we have made an assumption that this specific solution pair is the one that minimizes the sum of, its numbers, right? So we're going to proceed with this assumption. Now we can multiply both sides by q squared, giving us 2q squared is equal to p squared. Okay? So now observe this. Because p squared is equal to 2 times something, then this would mean that p or p squared is even, right? But if p squared is even, then this would mean that p itself is even. So in fact, I could have just written p itself, but I wanted to kind of explain, okay? So p is even. So therefore, we have that p is equal to 2 times m, where m is some integer. And this would, by the way, mean that m is equal to p over 2. So now notice this. We can substitute p equals to 2m into this equation. This would give us 2q squared is equal to 4m squared, right? Now we can divide both sides by 2, giving us 2m squared is equal to q squared. Now pay attention to this. I'm going to take my purple marker and I'm going to label the two equations, this one, equation 1, and this one as equation 2. Now notice that equations 1 and 2 are basically the same equations. It's just that the letters are different. And so they are symmetrical. Now because this particular equation corresponded to the solution pair PQ, this particular equation by symmetry corresponds to the solution pair QM. But wait a minute, if it's QM, then let's see what the sum of its contents is. The sum of its contents, this would be Q plus M. But because M is equal to P over 2, then we can replace it with P over 2. So P over 2. Now, observe this. Which one is smaller? P plus Q or Q plus P over 2? Well, it's obviously this one, because this one we have P, and this one is P over 2, and we still have a Q on, in both sums. So therefore, this one is actually the smaller sum, but we claimed that this was the smaller sum. So we have a contradiction. Now, I'm going to show you that it's possible to go infinitely smaller than this sum. That's right, this is not the end. So we're going to again observe that 2 times something is equal to q squared, and therefore q squared is even, so q itself is even. So therefore, q is even, it's equal to 2 times something. And this would mean that n is equal to, so it's 2 times n, and n is equal to q divided by 2. Now I'm going to substitute the result of q equals to 2n into this equation. So I'm going to use this side of the board. Substituting this into here would yield 2m squared is equal to 4n squared, right? So 4n squared. 4n squared. And dividing both sides by 2 gives us 2n squared is equal to m squared. Now notice that this equation, which I'll label as equation 3, is again symmetrical to equations 1 and 2, just with different variables, right? So therefore, this equation corresponds to the solution pair mn. And what is the sum of its contents? Well, it is m plus n, and m, as we saw earlier, was equal to p divided by 2. So this over here is p divided by 2, and n over here is q divided by 2. So that would be q divided by 2. Now, notice that we have a sum over here, and this sum is okay, I'm so sorry about that. So p divided by 2 plus q divided by 2. This sum is even smaller than q plus p over 2, right? Which is even smaller than p plus q. And notice that again over here, m squared is equal to 2 times something, so m squared is even. M is even. And you can essentially let m equal to like 2b and do this process indefinitely and get smaller and smaller sums. But we claimed at the start that there was a minimum sum. So therefore, we have derived a contradiction. And therefore, this claim of a minimal sum is not true. There is no minimal sum. But because this is not true, and therefore, root of 2 is irrational. It is not rational. Now, I think this was very cool, but the proof technique is what I was really trying to share. This concept of an infinite descent is super powerful. It can be used to show that no solutions, or maybe no type of solution exists, such as integer solutions, right? You can maybe assume some sort of assumption, and then you can prove that it's possible to get this assumption to infinite degrees. But if this assumption is finitely bounded, then obviously, if it goes to infinite degrees, then this assumption is false, and therefore this claim itself is false. And that's the basic technique of infinite descent. It's really cool. I highly recommend you check this out and study it for yourself. It's super useful for many contest questions, actually, if you're into math competitions. So that's going to be it for this video. I hope you learned something new. I hope you found this video interesting. If you did, then please do consider dropping a like and subscribing. Thank you very much. Bye.